So this will be the beginning of video 2 for section 4.4. We're picking things up on number 10, and right now we're just going to set up the problems. So 10 says we're going to make a fence around a pea patch, and it's going to be enclosed by a fence, but it's also going to be divided into two parts by another fence parallel to one of the sides. So I think I've drawn the picture there on number 10, the way it's describing it. What dimensions of the outer rectangle will require the smallest total length of fence? How much fence will be needed? So I've set it up as W, and then L will be this full length. And so they would like us to maximize the area. What dimensions of the outer rectangle will require the smallest total length of fence? Okay, no, I'm wrong. We actually know the area is going to be 216. We want the smallest use of fence. So I'll call that perimeter, even though it won't be a true perimeter. To fence all of this in, I'm going to need 2 L's for the top and the bottom, and then I'm going to need 3 W's. And so I want to minimize the amount of fence I use. In other words, I want the smallest P possible. But this thing still has to have the area that they gave me of 216 square meters. I know that the area of the whole thing will be length times width. And so now I can convert. And it doesn't really matter. I'll make it say, let's go with L equals. So L equals 216 over W. And so now I can convert. Perimeter equals 2 times 216 over W plus 3W. Perimeter equals, let's see, 2 times 16, that's going to be 432 over W plus 3W. So there is my equation I need to minimize. All right, moving on to 13. 13 says we're going to design a poster, and it's going to be rectangular, and it's going to have 50 square inches of printing, so just the inside. And then it's going to have some margins, so it's going to have a 4-inch margin at the top and a 2-inch margin at the side. So this length is 4, that length is 2. What overall dimensions will minimize the amount of paper used? So while we're talking about simply the printing on the inside, we want to know what will be the overall dimensions of the poster. So we have some choices in how we want to do this, and either one will work. One might prove to be easier math, but let's just get started and see where we go. So I'll just call the W will be the length of the entire piece of paper, and we'll call L the length of the entire piece. And they would like us to, what overall dimensions will minimize the amount of paper used? So we're talking about area, length times width. So this is what I want to minimize. And so I need to convert one variable into the next. Okay, so the way I've set this up then, let's now take a look at the known quantity we have, and that would be that the area of the inside is going to be 50 square inches. So let's see what we can do with that. So I'm going to write another area equation. I'm going to say area 1 for the inside. And I know that according to my dimensions here, if the whole thing is W, then the width of the smaller area would be W minus 2 for this margin and 2 for that margin. So I know that this length here is W minus 4, and then this length would be L minus 8. So I know that the area is going to be W minus 4 times L minus 8. And so before I can convert, looks like I need to maybe clean this up a little bit. And this is going to get pretty nasty. So let's stop and pause for a minute and see if there's anything I've missed. It's looking like conversion here is going to be kind of nasty. So I think what we're going to do is we're going to change our strategy. So let's come back, and before I erase this, let's do what I'm thinking, and then we can compare the two, and you'll see why I decided to do it the way I did. So let's try it. I'll do this in blue. Let's try making this length L instead. And then let's make this length W. In which case, my objective function now becomes, I still want to maximize area, but now area was going to be W plus 4 times L, which is the length of the inside, plus 8. Alright, so this is now the equation I want to maximize, or minimize in this case. And then my conversion equation would now be A equals length times width, so just the inside, and I know that length times width has to equal 50. And now I can easily solve for L or W. I'll just pick W for no reason. So I get 50 over L. So now I can come back to my area equation, plug in W, giving me 50 over L plus 4 times L plus 8. And so now, clearly it needs to be simplified a bit, but I have an output based on a single input of L. And notice how much easier that conversion was, which we could then plug in, compared to the mess that we were about to make here, foiling this out and then trying to get either W or L by itself was going to be a nightmare. So I think we'll stick with the blue plan, which means I'm just going to get rid of the red so that we do not get confused. Alright. And I think I'm going to have to just leave this W minus 4. L. Okay. So there we go. And we'll come back and finish that question. So now we go on to number 15, and that'll be the last one on this video. And this one's a little bit weird because they gave us an A and a B, and the A and the B don't matter. So let's read the question real quick. Two sides of a triangle have lengths A and B, and the angle between them is theta. What value of theta will maximize the triangle's area? So the only input, the only thing that's changing is theta. So whatever A and B are going to be for this triangle, then they're going to be constant. So we're not changing the angle, and we're changing values of A and B. It's just changing theta. So what that means is they want to maximize area, and so we have area equals 1/2 A B sine of theta. And while this may look like all of the other equations and I have too many inputs, I really only have the one input. So for all practical purposes, we wouldn't necessarily want to do this as a proof, but if this was bothering you about the A and the B, you could sort of just make up your own values and see how the problem's going to act, and then you could come back and leave A and B and see what happens. So in the third video, I think I'll go through and selectively solve some of these problems, or at least start some of these problems. I will not be solving all of them. Okay, so this is the end of the setup for the first 15 questions.